morning, everyone. And this technical section I will be talking about clays, which are most promising and potential material, and we need to know about this kind of soil. So I will be stressing on what are clays, how are they formed, their structural criteria, as well as in their origin lies the history of the exploration, connectivity, as well as mining and sampling of these clay minerals. So clay minerals, they are called as sometimes mineral term and size term and rock term because they have a less than 2 micron particle size. They are rock term because associated with sedimentary rocks, and mineral term because they are composed of clay minerals. So these are soft, freely bound, fine-grained material which have a high plasticity, and they are hydrous aluminum phyllosilicate. It means that they have a layer-like structure. So when we were kids, we played with the mud, and we know that what is the clay. So there is a distinction between the clay and the silt on the basis of the particle size as well as their texture. Texture is the relative distribution of cations and ions in the clay, whereas the particle size is for clay is less than 2 micron. So chemistry of clay it's a complex mixture of cations and anions and combination of different minerals which are joined into a sheet-like structure. We know a property of plasticity of clay, which is just the property of deformation of clay without affecting him under the action of external forces. So we can see that there are two layers of water molecules which are absorbed on the clay. This is due to the process called adsorption, which let clay particles to slide apart against each other. When these external forces are removed, the clay come back to the normal position. So this is the criteria to differentiate between the silt and clay in the field. So we talked about plasticity. So why so? What is the reason behind this plasticity? It is due to the presence of negative charge along the cationic edge. So what happens? If we go to the molecular level, we can see that there is always a unshared oxygen atoms along the edge of the continuous chain. And along that edge, we always have a negative charge. This is the reason why these clays have a negative charge. So if you talk about the tetrahedral structure, sometimes what can happen? The tetrahedral is composed of silica tetrahedral, which has 4 oxygen atoms surrounded by it, and sometimes magnesia, which has a lower valence cation, substitute for the higher valence cation, which led to the formation of net charge of -2. And this is the reason why these clays are negative and they imbibe water in their layered structure. So this is the basic structure unit for clays, which is consist of tetrahedral and octahedral, which are joined together to form tetrahedral and octahedral sheets. Sheets are joined together to form layers, and they are separated by interlayers, cations, anions, and water molecules. So we have basic structure unit of octahedra. In the octahedral layer, if we have magnesium in there as the dominant interlayer cation, it is called as sprucite layer. When we have alumina in place of magnesium, then it is called as gibbsite layer. So because of interplay of these cations and anionic substitution, we have different type of clay in the nature. So there are 3 types of clays we generally form in different environmental conditions. We have silicate clays which are 1:1 and 2:1, and these are generally formed in the plethora of locations across the world. And when we talk about subsidized type of clays, they are generally formed associated with ancient soils like altisols and oxysols. And amorphous clays, they are generally formed by crystallization from the amorphous material or from the volcanic glass. This is a structure model for 1:1 and 2:1 clay. We can see that 1:1 clay have a simple structural criteria consisting of one tetrahedral sheet, which is attached by the apical oxygen to the octahedral sheet, forming a ratio of 1:1. And we have 2:1 clay minerals which have octahedral sheets, which is sandwiched between the 2 tetrahedral layers and which are joined by the apical oxygen. So having a structure architecture of repeating structure units. And these are types of silicate clays. We have 1:1 and 2:1, and for our purpose, for the production of LC3, 1:1 clays are considered as most important clays. But now, for recent research has conducted, which shows that 2:1 clay consisting of monopolarite, stepolite, and smectite, they are also used for the production of LC3. So we have different grades of kaolinite which are collected from different environmental conditions. We have kaolinite which are rich in iron, having iron impurity sometimes in the mine. These clays are as a discarded material due to some impurities of titanium or iron. So these clays can be used for manufacture of NC3 as they have medium to moderate rate of kaolinite content. Sometimes we have kaolinite and smectite layers, which is the intermediate process in the formation of smectite clay. So these clays which having the layers of smectite in the kaolinite, they can also be used in the formation of NC3. So this is the kaolinite structure. I am not going to discuss the structure of kaolinite. We already have discussed. But the thing is, we know that kaolinite is one of the 6 most abundant mineral in the earth crust. And it is generally found along the equatorial belt, Madagascar, India, Africa and Australia. So the best place to locate this place is to found around these areas. We have elite clays. These are typical clays of lacustrine or marine climatic condition. So they are of other types, glauconite, which are green in color, celadonite, which are iron-rich elite. So what happens with these clays? They are very strongly bonded because the hydrogen potassium is occupied by the interlaced spaces between these clays, which don't allow waters to enter into their structure. Hence, these clays are not sufficient for pozzolanic activity. We have smectite clays, which are very good clays for which have a very good isomorphic substitution, and the layers of these clays are held by van der Waals forces, which allows water to enter the structure. Hence, these clays become always ready to take water into their structure. And when you see the structure which are always cracking, this is due to smectite clay. And the best area to find this clay is the semi-arid climatic condition where drainage pattern is very poor. So naturally we have in India, Rajasthan area or some arid regions of Gujarat. So we can find smectite clay in those areas. So how these clays are formed? We talk about clays, how these are formed in nature. There are 3 processes how these clays are formed. One is inheritance, that is weathering of the clays, weathering from the parent rock, switching out the material like ions and cations from the parent rock, and the precipitation and crystallization of that material to form new type of clay. We have transformation process, which resulted in the formation of clays by the process of hydrothermal activity in a high energy environment. We have new form clays, which is formed by the direct precipitation from the solution or from the volcanic glass as well as the volcanic ash. So the conditions for the formation of clays, yes, we need a parent rock which alters and form secondary clay mineral deposits under different climatic conditions. We need agents of weathering in different environmental conditions. If we talk about alien environment condition, that is more dominant in arid climatic condition. In humid climate, the water is the most important agent, and sometimes organisms, humic acid, folic acid, they are also responsible for the weathering of the clay minerals. So reaction times is a very important factor. The materials which are leached from the clays, they are need us time to recrystallize at a particular place and deposit at a particular place. So it's very important factor, time, which led to the formation of these clay deposits. So we have geological agents. We talked about air and water in different environmental conditions. Apart from this, we have a climate, which is very important for the formation of clay. Every clay is formed in a particular type of environment condition, but it is not necessary. Sometimes within the same environment, you can have a different type of clay minerals due to different pH, acidity, as well as different alkalization of the root material. So climate determines if the seasonal distribution of rainfall is good, then the percolation of material is more, so it leads to more leaching, more weathering of material, so the formation of clay is more pronounced in humid climatic condition. And if we talk about topography, it is always very important for the finding of these clay minerals. Naturally, topography with very low vegetation, they don't allow water to percolate. So no organic acid, so no formation of clay minerals. So it's not necessary you find clay minerals in the desertic or arid climatic condition unless they are formed by precipitation from the volcanic ash processes. So pressure and temperature are very important for the formation of clay minerals. You know, some clay minerals which are transferred from one to another clay minerals. Suppose we have kaolinite clay minerals which are formed at the earth's surface by weathering processes. Due to high temperature and pressure conditions, these clays are transformed into dicite and finally they transform into illite. So geologists should be very expert to know about these conditions which are widespread in different environments to locate those clays which are very economically viable. Of course, we need a depositional setting from where these clays are transported and then deposited in a particular environment. We have lake setting, we have marine setting, continental setting, as well as we have volcanic setting. So why weathering? Why this process of weathering? Why it happens? This is due to instability of the parent material. As a general rule of thumb, we know that the minerals which crystallize at a high temperature pressure condition, when they are exposed at the condition near the Earth's surface, they are susceptible to weathering. They lost their ions and resulted in the form of change in their structure, and the lesser ions which result in the form of clay or clay minerals which are of secondary origin. So two processes which are very important for the formation of clay minerals. One is physical weathering, another is chemical weathering. So towards the right top you can see, left top you can see the sandy beaches which we see today. They were once quartz or feldspar. So due to weathering effect, they have been eroded by the stream or the action of river and deposited at the site of deposition as a clay or sandbeds. So why it happens? It is due to the process called abrasion, which is in the arid climatic condition, by the action of physical scraping of the rock by plant, wind, water, etc., even gravity also. And frost weathering is the decomposition of the clay mineral due to, especially in the snow-capped area where the ice exerts pressure on the rocks and the rocks break apart. And we have thermal expansion. This is due to variation in day, night, summer and winter. This weaken the molecular level of the rock and the rocks breaks apart. So the chemical weathering you can see on the right top, the effect of chemical weathering on the 100-year-old statue, which has been changed and altered due to the effect of hydrolysis. Hydrolysis is a process when the rainwater reacts with carbon dioxide and it starts leaching the rock material, so that rock alters and breaks apart and the composition changed totally. So oxidation process is a process of making the rocks leach by the interaction of atmospheric oxygen with the iron-containing rock formations. So we have seen many caves. We have Bora caves in the Visakhapatnam cave in northern part of India. They are formed by the process of carbonation. In carbonation process, what happens when the rock reacts with the water, which are carbonate in nature, and the carbonic acid is a weak acid, and we start leaching out carbonate from that limestone terrain or dolomitic terrain. So it results in the formation of caves or halos, which are resultant formation of these caves and halos in different parts of the world. So two reactions which are important for alteration of clay minerals. One is combinant reaction. For example, some clays are formed from this one clay by simple dissolution of that clay particles into the solution. It is called as combinant reactions. So new formation is a process of formation of clay by simple dissolution and precipitation from the solution. This process or mechanism generally takes place in the environment of high fluid intensity, as well as it depends upon the crystallization chemical mineral of the fluid. So it is of two types, epitaxy and topotexy. Epitaxy means epi mean upon and taxi mean arrangement. It is just the arrangement of crystals on the substrate so that they are repeated in similar fashion that they follow the crystal that is of their base substrate. So it may be of two types. Homotaxy, epitaxy is just suppose we have silica layers which are overlain by the silica substrate. So this is called as homotaxy. For this process, we have formation of similar type of clay minerals, and we have heterotopotaxy. We have one clay mineral, and over that we have growth of some other crystallographic species of mineral. Then it is called as heterotopotaxy. So topotaxy is just suppose we have fissures or breakage in the rock. So sometimes minerals are derived from that rock. It is called as topotaxy, and it is not necessary that precipitation on pre-existing surface takes place. It can take place at any environment, any weak fractures or weak zones. So incombinant reactions, as contrast with combinant reaction, these reactions are very important for the formation of clay minerals. On your screen, you can see sodium albite. Sodium albite is a type of mineral which is precipitate in nature, and due to when this mineral reacts with carbon dioxide and water, and it answers into kyanite minerals, silicic acid, as well as quartz and carbonate minerals. So this is a very important process for the formation of clay minerals in the areas where we have high pH and pH conditions. The most important reaction in the formation of clay minerals are acid-base reactions. Before we get into acid-base reaction, we must know the basic chemistry that every single drop of rainwater contains dissolved gases. It may be carbon dioxide, oxygen, argon, or nitrogen. So when these gases react with water containing these gases react with rock, they start leaching out material from the rock, and there are two processes: chemical weathering of albite as the chemical weathering of feldspar, which make different type of clay mineral within a similar environment, that is hot and humid climatic conditions. Due to the formation of these clay minerals, we have plenty of clay minerals within the same environment. And further, the biological activity into the deeper substrate releases further carbon dioxide, which reacts with the water table near the groundwater. So, leaching it minerals near that aquifer and start leaching those minerals and alter those primary rock into clay minerals. So, hydrothermal activity on the top right, you can see your alteration halo diagram. This diagram represents alteration halo. What are these? These are special signatures on the field. Sometimes while doing field work, we came across these special features which tells about the mysterious condition of the movement of hot fluid. And what happens when the hydrothermal fluid during its journey from the Earth's interior to the Earth's surface, they pass through the different type of rock minerals and they alter those rocks into clay minerals. So we have different types of clay minerals which are along the boundary of the alteration halos, which is called as argonic zone. So these are best indicator in the field where hydrothermal activity is related to find those type of clay minerals. And we can see that in this diagram that one clay is transformed into another clay during hydrothermal activity. We have big pseudo-hexagonal plates of kelenite which have been transformed into illite by the effect of hydrothermal alteration. So the best mechanism for hydrothermal alteration is the ion exchange. The ions are exchanged between the fluid and those of the environment. And it may be by layer transformation also, where whole layers are transformed from one to another. So we have collected clay from different environmental conditions. Primary clay minerals. Primary clay minerals are those minerals which are you can find everywhere on the earth. So you go to the host rock, you can find they have been altered into clay minerals. So it's quite easy to find this type of minerals. But secondary clays are sometimes very challenging to find those clay minerals. What we do, we generally find the deposition mechanism and the residual platform. We find along the river beds and embankments and deposit it under some deltas. These clay minerals are widespread in those areas. So we have diagenetic clays which are found in deeper environmental condition and high temperature and pressure condition. Generally, the diagenetic clays are not kelonitic clays; they are transformed into chlorite or sometimes illite. So sixotized clays which are associated with alpisols rocks. So we have so many alpisols and oxysols rocks throughout India. They are best sites for the prospecting for kelonite clay. We have clays which are also formed from the volcanic ash. We have volcanic activity in India, Deccan Trap. All over the world we have volcanic activity. So in the Pir Panjal area of Kashmir, so due to alteration of this volcanic ash, we have formation of smectite clays. And further, after a period of time, sometimes if the environmental conditions are favorable, these smectites are altered into kelonite clays. We have hydrothermal clays which are formed by the alteration halos. They are important signatures which indicates that hydrothermal activity. You can find this hydrothermal activity on based of some signature also like geysers, hot springs. If you have hot springs in your area, then there will be some places you can find this hydrothermal type of place. So exploration. So exploration is the process by which geologists explore these clay minerals. It seems quite easy, but exploration process takes a lot of time, energy, and even after them, exploration programs are not always successful. It requires a wide range of survey from the dextrose survey in the initial phase and finally the baseline survey. So during the dextrose survey, what we really do, we can grab whatever information we need to study. As far as we have geological maps, we have satellite images, we have literature, and other reports which are required for the exploring these clay mineral deposits. So at the end we can decide whether we can move with the project or give it a green light or stop the project. So, but sometimes it happens, the desktop survey, the information we collected from that survey is sometimes outdated. So for that purpose, we have to visit the field to get the baseline surveys. So baseline surveys involves our direct interaction with the rocks in the field, and from there we can have the direct idea how these rocks are altered and where to find those minerals of economic grade. Exploration is a game of probability. Suppose we have 100 discoveries, and out of those 100, 50 becomes promising. And sometimes from that promising discoveries, we have 10 which are becomes our project. And based on their feasibility study, that may be technical, environmental impacts, legal feasibility, we have only one mind. So geology should be patient while exploring these places. Sometimes they become very challenging. In my experience, I explored few clay deposits, but after then I came to know that they are under some environmental act, so it's very hard sometimes. So we have many geological problems in this field. Sometimes Professor Sharma sends us to explore clays in some snow-capped areas. It is very hard to explore clays in those areas. First, we have to remove the layers of ice sheets from that area, and after that we can achieve those clay minerals. So it's very tough to in this clay mineral. We have a specific rock on the Earth's surface which are called as cratons. Cratons are a stable part of the Earth crust and they are found everywhere on the world. So what are these cratons? These cratons, they are crystalline rocks, they are most buoyant rock, and they are 3.35 billion year old rock. So how is it possible that these cratons sustain until now, where the process of Earth is always in the formation of construction and destruction? So this is due to their buoyancy and their viscous nature. So if we compare this craton on the globe map of the world and the clay distribution along the world map, we can find that most of the clay minerals of smectite and kieranite, they are distributed along the cratonic belts of the India. Of course, we have some clays from the cold belt of India, from the mountainous region, Himalayas, but they are not very much proposed as when compared to the cratonic clay minerals. So, just stick on this concept, we have explored clay from the Indian subcontinent. We know that Indian subcontinent consists of several cratonic nuclei, carbon craton, single craton in the east, and in the center Bhumidhar craton, and obviously Aravalli Giri hold that in the northern region. So what we find that most of the clay minerals, they are associated with the cratonic regions of India. So the best place to locate primary or secondary clays, mostly kilolitic clays, is to find them on the cratonic areas. So we have advanced exploration techniques which involves visual inspection of the data, acquiring the data set, which helps in minimal cost and efficiency in getting those minerals and mines. And we use drones for better picture, 3D spacing, as well as accurate mapping of that area. So drones are nowadays using in every step of mining, starting from exploration to the blasting of the mine. So they are very important. So these are modern techniques, and geoscientists should be very expert in grabbing those virtues and finding those situations where to find these type of clay minerals, and we should know the geological concept where to find a particular type of clay minerals within different environmental settings. So what these add up to? Yes, demand growth is real and we need to explore new deposits by using the modern as well as our traditional techniques, and which includes the field observation. Field observation is the primary and the most important part of geology. Everything starts with field and ends up with the field. And in collaboration with geosciences, that is the geochemistry should be known in order to interpret what are the clay minerals, what is the composition, are they suitable for making particular type of clay or limestone or not. So we have data science, which is very important. Together we can make a sense to achieve the target. So sometimes we have situations where in the field we have some hazards, we are unable to find clay minerals. Suppose towards the top right hand side you have a coven grass. We were in the field and we have a condition like very heavy rainfall, peak precipitation time, and we were unable to find anything on the field because of waterlogging. And we had only 2 days to explore clay minerals. At this situation, what we did, we saw a coconut grass. It was an accidental discovery. We saw coconut grass with their roots, some patchy white colored material. What we did, we started digging that material, and what we found there are clay layers. So I know the concept of geobotany, that some plants are important indicators of specific minerals. So same plant was targeted in different parts of the world. So what we found that the special case with these type of common grass is they always grow in a colony over a large wide area, and they don't allow other species to enter to their territory. So over a large area we found clay deposits from different parts of the world. So it's better to ask this plant as an indicator of clay minerals. And when we came back to our IIT Delhi, we have a depth survey on these plants. But we found that these grasses are found in a heavy loamy soil, which is rich in clay, especially kyanite and smectite clay. On the left top, we have an ant hill. Ants are architects in the earth crust. What they do, they catch the clay particles and mix them with the organic acid and some other ants and make their hills, which is the process by bioturbation. So, in the area of heavy semi-arid conditions, we are unable to find anything, and at that time, ant hill was the only hope to find clay deposits. And after this, we found this ant hill in some other area, and again we found clay minerals beneath the earth crust. We have artificial hollows. We already discussed that. Suppose we go to doctor and doctor see our symptoms and he gives us medicines. Based upon this, he can detect our disease. Similarly, a geoscientist can see the symptoms in the earth, alteration, etc., and he tells about the conditions of the earth beneath. So similarly, by this seeing this alteration, we can to know that clay minerals which are formed by the alteration of smectite via kyanite, smectite, and finally to kyanite. We have mud cracks in the arid climate condition, no precipitation, and the rock become very endurable. As such climatic condition, we found that mud cracks, and the mud cracks are very important indicators of the material underlying the earth crust. And when we start digging these mud cracks from two different areas, one from Senegal and one from eastern part of India, we found that 35-meter deep clay deposits were found, which were kyanite as well as smectic in nature. So sometimes in the field, geological work is very tiring, and sometimes nature gives us some rewards. So while doing field work, we get these rewards. During my geological journey, I got so many rewards, but unfortunately, when I came to Delhi, my mother threw some of these rewards, and for her, these are only stones. So it was very disappointing moment for me, but still we are again collecting these samples, these beautiful reports for. So we have some geotechnical strategies which are applied in the field to differentiate between mud, soil, silt and sand as well as clay. So we have manual test, we have visual test. Visual test involve general visual visualization of the sample, granularity, their luster, their texture. Just take the sample in the hand, feel the texture, what you feel the more. If you feel the sand more, that is a sandy clay. If you feel clay, that is a clay. So it's just not a rocket science, it's a basic case. So we have manual tests which are the plasticity of the clay. So we'll discuss this test one by one. We have dry stem tests. Okay, we have to take some clay mineral in our hand, and if we are unable to break those lumps, then it is a natural clay. But it becomes powdery, that is a silt. But sometimes considerable finger is required to break it. It is a silt, but it has a clay content in it. So from this test, we can differentiate between the clay, silt, sand, and clay silt. So deltency test, this is also important test. So what happens that silt is permeable in nature. When we pour water in the silt, it should glossy texture. But same when we do with the clay mineral, they absorb water. So these are simple tests which can be performed in field to differentiate between agricultural soil as well as clay soil. So we have ribbon and thread test. Take some water in your hand, make it workable, add some clay and make a ribbon out of it. If you are able to form a long ribbon, then it is definitely a clay, and if the ribbon break apart, it is not a clay, it's a silky clay. And similarly, we take clay and press it between the thumb and the middle finger to form a ribbon of about 3 mm. And let this ribbon break it to its own weight. If it is making a ribbon of considerable length, then it is a very good clay. If we have less ribbon, then it is a clay mixed with some silky material. But those materials can also be used for making LCP cement. So we have made some soil capture on hand. We have, if we have bolus ribbon, which is little bit silky in nature, we have 20 to 25% of clay in it. And we have sandy clay loam, which are strongly bolus and containing sandy in touch. We have sandy clay. And if we have clay loam, they contain marginal keronite or smectite content. They form still a good ribbon, so they can also be used. And we have sandy clay. They are clay, but they have still some particles of sand, so they can also be used for our purpose. We have light clay and medium and heavy clay, which are having a plasticity in nature. They form a ribbon, and when you touch them, they have a good texture of clay material. Then it is called as clay. So these last three clays, they are very important as they contain moderate to high keronite content. So while in field, sometimes we encounter that high-grade keronite are found associated with low to medium-grade keronite within the same mine. So these heaps are discarded by the plant due to some impurities which make them unfit for use in ceramics and paint industry. So we can use these clay minerals for the formation of LCP cement. So they are just found in the same mine. So sampling methods, two types of methods, probability sampling. If we have the same material within the same mine, based on the color, texture and granularity, then we need not to collect so many samples from the field. Only 2 or 1 samples are sufficient. But on the right hand side, you can see a picture within the same mine. We have 3 different types of material: ferruginous, red ochre, and keronitic clay. So in this case, we have to collect all these samples, because when we collected these samples, we found that 3 of these samples were clay. The red sample was 45% keronite, and the light yellow sample, they have 55% keronite content, and naturally the white sample is 78% keronite content. So these are discarded heaps from the mine, which can be used for making LCT. So best method is to follow each chapter procedure where samples should be collected in an unbiased manner. We should not collect samples which are looking very good. We can grab this sample, they are white in color. We should have a homogeneous sample so that it will be good for your future perspective. So the best strategy is to collect the in situ samples. Sometimes we collect samples from a far distance. It's not a good strategy. We have to find the sample from the place where it has been locked. So for clay mineral exploration, we have open cast mining. Mining has been an integral part of human civilization since a time immemorial, providing us raw material for making homes. So for clay minerals, open cast mining involves removal of the external layers and exposing of the internal layers of material from the earth crust. In open cast mining, clays are generally mined in a series of benches where clays are extracted and they are used for purpose. So we have different strategies which are to be followed in open cast mining, because open cast mining there is a challenge of deforestation, pollution. So there are some standards to mitigate these problems. These should be followed very accurately. So finally we have samples. Samples should be packed in Ziploc bag. They should be covered and marked with proper orientation to avoid confusion. And finally, they should be marked with felt tip marker so that they can't fade it when they are transported. So this is the important strategy how we do what to perform in the field, from the collecting of clays to the packing and then transporting for the lab test. And with the lab test, we will do the geochemical analysis as well as their geological analysis. Thank you.